Let me start off with something to wake you up. So here's like a warm-up exercise. Problem 10 from your text. A is an m by n matrix, and let's say that the rank of A is n. And suppose A of some vector equals A of some other vector. So you've got these two vectors, does that imply that the vectors are equal? Does that imply that the vectors are equal? If AC equals AD, does that mean that C equals C? Okay, so think about it for 2 minutes. Okay, talk to somebody nearby and say what you're thinking.
Does this mean that A equals 0? If the rank of A equals 0, I feel like this might be taking a jump that you can't make. I feel like it's too easy, and so I want to say no.
But like, because like, I think
So
if we think
so
about it,
the range equals the number of pivots.
or like even
It was it's the number of pivots is the number.
Okay, who has an idea? Anybody have an idea? Raise your hand if you have an idea. Only Elena has an idea? Is that true?
Wait, is this to clarify that A doesn't equal 0? It can't be the 0 matrix.
Well, I mean, the rank is n, right?
But N can equal 0.
It's an m by n matrix.
Okay.
Right? Yeah. Okay. So, Andrew, what do you think? Any ideas? Like, what theorem or what facts do you think might be relevant? So right, here's this thing. You want to think like, what comes to mind, right? What ideas? What you should almost like when you write essays, you do a brainstorm, right? You throw down just all sorts of ideas. I think this might be related. This might be related. You throw out things that might be related. What might be related? Anand.
I was just thinking that, so suppose you take AC, so you would get a matrix which is m by 1 probably. No, sorry, m by. So suppose C is
Yeah, C is going to be an n. C is going to be n by 1, right?
Yeah.
Right, it's an n vector.
So then you would get AC would be an m by 1 matrix, and you would have to get AC would probably equal to the row matrices times C. So it would be a linear combination.
Okay, so you're saying that on the left-hand side, we're going to have C1, A1 plus C2, A2 plus C and A, C N, A N, and on the right hand, we're going to have D1, A1 plus D N, A N. That's true.
Yeah. So then in that case, yes,
Right? Okay. Yeah.
I can't really think of any theorems in particular, but just going back a little bit, a few days.
Yeah, sure.
Probably done that. So if we assume that A is, so all the rows of A are linearly independent.
Yeah, right, because the rank, the rank is
of
n,
course, yeah.
right? The rank is n, so that tells you that, right, there are m rows and n columns, right? Well, the rank is the dimension of the column space as well as the dimension of the row space. Say. So in particular, you know that the columns of A are linearly independent.
Yeah, so in that case, for the left hand side to be equal to the right hand side, either all C1, C2, Cn and D1 to Dn would have to be 0, or C1 would have to equal D1, C2 would have to equal D2.
That's the second statement you made encompasses the first.
Okay.
Right? If you say either they're all equal to 0 or C1 equals D1, C2 equals D2. If they're all 0, certainly C1 equals D1 and D2. So you don't need to say either they're all equal to 0 or they're all equal to each other. Just say they're all equal to each other.
Okay.
Yeah. So by because of the linear independence of the AI, right? The rank is n, so that tells you that the columns are independent. Columns independent tells you that each thing has only each linear combination has only one way of being attained. So if these two linear combinations are equal to each other, then they must be the same linear combination. Right? The coefficients must be identical. Okay, so that's certainly one way to do it. You say AC equals AD. That tells us this. Since the rank is n, we know that the columns of A are independent. Right? Columns A being independent tells you that, for example, if I subtract both sides, C1 minus D1, that tells you that C1 must equal to D1, and C2 must equal to D2, and Cn must equal to Dn, since any linear combination of the AI has a unique expression. Right? Here we have a linear combination, and we're saying that that's equal to this linear combination. Well, because of linear independence, the expression must be, this expression is unique, right? So the coefficients must be equal to each other. Okay, so that's certainly good. That's like getting down into it. Elena, what were you thinking?
Well, we know that the rank plus the nullity is
Okay.
the number of columns.
Great. So we know that, or by the rank theorem, we know that rank plus nullity equals number of columns, which is n. Right? and the rank is n, that tells us that the nullity is 0, right? In other words, the dimension of the null space of A is 0, right? So the null space then, right? The null space of A is just the 0 vector, right? So then,
So then suppose AC equals AD, so then AC minus AD equals 0. Factor out the A. And you know that C minus D has to equal 0. So then C has to equal D.
right, right, right. We know that AC equals AD, right? AC equals AD. So A times C minus D is 0, right? That means that C minus D is in the null space. So C minus D is equal to 0. C minus D is in the null space. Okay. So C minus D is equal to 0. Okay. So one way you do it by getting into it with your sort of bare hands. The other way, you're going to invoke some machinery that basically uses this. Right? We constructed the rank theorem from our knowledge of linear independence. So however you want to do it, either way is okay. Okay. Any questions? Any questions? Okay. So if we were writing this out formally, we'd say by the rank theorem, this plus this equals n. So nullity is 0 since rank A equals n. We know that the nullity of A is equal to 0. In other words, the dimension of the null space is 0. That tells us the null space is the 0 element. Since AC equals AD, AC minus D is equal to 0. That is CD is in the null space, so C minus D equals 0. In other words, C equals D. Right, so when you're writing out a proof, you add some transition words to indicate, what you're doing, and you add things like this, like if this implies that, or this is equivalent to that. Sometimes when I see proofs on exams, all these things are left out. It's like some of the things are left out, and then it's not clear. Sometimes it's not clear if what the argument is. Like all the pieces are there, but the line of the argument is not made clear. So it's necessary to write as if one were writing an essay, basically, a very simplistic sort of essay. But yeah, that has to be included. The relations between statements have to be included. Okay. So today we're going to enter chapter 4, which is basically the true topic of linear algebra. Okay, so up until this point, you haven't been doing what maybe we haven't reached really the real thing that you actually want to study in linear algebra. Today we will, and the object of interest is something called linear transformation. So linear transformations, and so now we can finally start talking about linear algebra. Suppose you have two vector spaces, V and W, and you have a map T going from one to the other. Okay. If T of V1 plus V2 equals T of V1 plus T of V2, for all v1, v2 in V. And T of alpha v1 equals, I should just say alpha v, equals alpha T of v for all alpha in your field and v in your vector space. Then we say T is a linear transformation from V to W. So this is the definition of linear transformation. What it does, what these two statements say is, what these two statements require, is that the map preserve the vector space structure. The map preserves the vector space structure, right? If you start off with a sum and you pump it through the map, what you get is a sum of the individual guys, right? V1 and V2 get mapped to, the sum T V1 plus V2 gets mapped to the sum T of V1 plus T of V2. Right? Similarly, if you take something and scale it, well, that's the same thing as if you mapped it over and then scaled it. Okay. So you're preserving the vector space structure, right? Or another way of saying that is that your map commutes. Your map commutes with the vector space operations, right? Here you've got vector addition. You can add first and then take the map, or you take the map and then add. You can scale first and then hit it with the map, or you can hit it with the map and then scale. Either way, you get the same thing. So it doesn't matter the order. You can vector space operations commute with the operation, with the transformation. Okay. So two ways of doing the same thing, right? T preserves the vector space structure, or T commutes with the vector space operations. Same thing. Okay. Okay. Bunch of examples. First, so the obvious one, let A be an n by n matrix. Right? Then, if we define a linear transformation, and I always use this abbreviation for transformation, X form and okay. Right, transformation. Okay. For some reason, this is an abbreviation that we always used as undergraduates, but I haven't seen it since then. And whenever I use it, people say, "What is that?" But I'm going to use it. It's easy. Transformation. Then we define a linear transformation P sub A going from Rn into Rm. Namely, right, you take the vector and then you hit it with. You take the vector and then you hit it with the matrix. Right. Right. A is an m by n matrix. Right. So you can use it to act on a vector in Rn, right? You hit the n by 1 vector, and you end up with an m by 1 vector, right? So it gives you AV, of course, is in Rm, right? So V is in Rn, and then AV is in Rm, right? Just by left multiplication. Right? You have your matrix, and then you hit a vector with it. You get a vector of different size. Right? So left multiplication is turns out to be a linear transformation, right? Why is this a linear transformation? Well, because if you take A of V1 plus V2, we know that that's A of V1 plus A of V2, and A of alpha V is alpha AB, right? We knew that from before, right? So this is a linear transformation. Okay, so any matrix determines a linear transformation. Number 2, let's make a map from L2 to L2, R2 to R2 that takes x1, x2 to x1 comma 0. Is this a linear transformation? Is this a linear transformation? Well, let's look at it, right? Is L of x1, x2 plus y1, y2 equal to L of x1, x2 plus L of y1, y2? Is L of alpha x1, alpha x2 the same thing as alpha times L of x1, x2? Yes, thank you. Finally, somebody nodded, right? Okay, right? L of L, right? x1, x2 plus y1, y2 is going to be x1 plus y1, x2 plus y2. And this thing says that you're going to get the first, you're going to get x1 plus y1 comma 0. Right? Is everyone okay with that? Right? You add these two things together, and you turn the second, the L transformation says just get rid of the y value and change it to 0. Okay. Over here, we're going to get x1 comma 0 plus y1 comma 0. Are those equal? Yes, they are equal. Okay. So preservation of the addition is okay. It's true. And here, we're going to get ax1 comma 0. Here, we're going to get a times x1 comma 0. Those are the same thing. So again, this is a linear transformation. Okay, right. The picture you have here is that this guy is projection onto the x-axis. Right? It takes in your vector and then returns the projection of that vector on the x-axis. Okay. Notice that L is the same thing as T of 1, 0, 0, 0. Right? If I take a vector, xy, and I hit it with this matrix, I get x0. Right? L could be realized as an instance of this first general class of linear transformations. Okay. Number 3. Again, we're going to be in from R2 to R2. Let L theta denote rotation by theta. Okay, maybe say counterclockwise. Okay, so it takes a vector and then rotates it counterclockwise by an angle theta. Okay. Is this a linear transformation? Is this a linear transformation? If you add two vectors and then you rotate them, is it the same thing as if you rotated those two vectors and then added them? Yeah, right? So. Okay. If you scale a vector and then rotate it, scale it and then rotate it, is it the same thing as if you rotate it and then scale it? Sure. Yeah. So both of these are true, and this is in fact a linear transformation. In fact, L can be realized as multiplication by left multiplication by the following matrix. This should lead you to ask, what?
I have a different question.
Okay.
Probably what you're looking for. Does it always have to be left multiplication?
Yes.
Okay.
Yes, right, because,
Because of the n by n?
yeah.
Okay.
Yeah. I mean, I guess you could make it, I mean, certainly if you multiply on the right, you could go from Rm into Rn, right? You could take somebody in Rm, a 1 by m guy. Basically, what you're doing is you're transposing everything.
Okay.
Okay. So, right, and then you multiply by m by n, and you'd end up with a 1 by n. But basically, you're just transposing everything.
Okay.
People, just out of convention, people usually do it the other way. Yeah, there's no reason for it. It's like right-handed or left-handed. Okay. So the question that I'm sort of fishing for is what? What's the question? Go ahead. You don't have to humor me. Just ask your own questions.
Okay, well,
Yes.
first of all, the determinant is 1, right?
Yeah.
Okay. I shouldn't have spoken up. But so then when you
Yeah, the determinant is 1. Yeah.
That train wasn't leaving the station. after
Okay.
that.
Okay, but that's a good train to ride, in the sense that, right? You remember, I don't know if I mentioned this, but what the determinant really tells you is about the how the matrix transforms area, right? How the matrix transforms area, and the determinant being 1 should mean that it doesn't do anything to area, right? On an infinitesimal level, right? And indeed, this guy doesn't do anything to area, right? Because all it does, if you apply it to some object, it will simply rotate it, not changing the area at all. Okay. Yeah. Whereas that one, you see, really affects area, right? Its determinant is 0, right? Because if you take some two-dimensional object and hit it with that guy, it collapses it down to a one-dimensional object in R2, which has 0 area. Okay. Yeah. And also invertibility, right? You can't go back to your original object once you've collapsed it all that way. But this one, has a determinant of 1, a non-zero determinant, and thus has an inverse. Its inverse will simply be rotation by negative theta. Right? You just put negative thetas in here, and that will reverse it and return you to your original object. Yes.
What exactly do you mean by a map?
Map, a function.
Just a function?
Yeah, a function. So a function that goes from one space to another space. A function. People use map and function basically interchangeably. Although functions are usually, if you're going from something into R, then usually people call that thing a function rather than a map. But it's basically interchangeable. Okay, so the question that I was hoping that somebody would ask is it true that every linear transformation can be realized as left multiplication by some matrix, right? We had this linear transformation. It turned out to be equivalent to left multiplication by some matrix. we have this other linear transformation, turns out to be equivalent to left multiplication by this matrix. Is it true that every linear transformation can be realized as left multiplication by some matrix? I'll leave that, I'm just going to leave that hanging there. So, can all linear transformations be realized as left multiplication by some matrices? Can all linear transformations be realized as matrices? Example number 4. We suppose we're in the polynomials of degree less than n. Okay. Remember, P sub n, polynomials degree less than n. Okay, and we think about D is differentiation. D is differentiation, right? D goes from Pn to Pn minus 1. Right? It's a map, certainly a map from this vector space to this vector space. Is it a linear transformation? Think for 10 seconds. What do you say? Chelsea? The question is, if you take the sum of polynomials and differentiate it, is it the same thing as differentiating the polynomial and then adding on to that?
Oh, yeah.
Right? Sure, right? If you take the sum of functions and you differentiate it, the derivative of a sum is going to be the sum of the derivatives, right? F plus g prime is f prime plus g prime, right? Second question, right? Is the derivative of a multiple of a polynomial the same thing as the multiple of the derivative of the polynomial? Right? In other words, if I have a function and I differentiate it, do I get just that number times the derivative? And the answer is yes. Right? These are properties that you know of differentiation, but maybe you didn't realize that that makes the derivative into a linear transformation. Okay. So then you should ask, what matrix? What's the matrix that corresponds to? That corresponds to differentiation. It should be, if what we think is correct, it should be that we can left multiply by some matrix somehow. There should be something like some sort of way of left multiplying by some matrix to get to differentiate a polynomial. Okay. Okay, so here are some basic consequences or properties of linear transformations. First, so again, you have t going from x going from v to w, a linear transformation. Then property number 1, the I'm sorry, I should call it L, as I have in my notes. L of the 0 vector of v turns into the 0 vector of w. So L preserves the 0 vector. Right? The 0 vector of the first space will become the 0 vector of the second space. Second, L preserves additive inverses. The additive inverse gets mapped to the additive inverse of the image. And these are some of these things that you don't like to prove because they're so sort of simple. Here's the proof of the first. Say, well, look, L of alpha v is, we know that L commutes with the scalar multiplication, and then take alpha to be 0. Zero the number. Right. Then that gives us L of 0 in the V space is 0 in the W space. Similarly, we know that L of V plus L of V minus is L of V minus V, which is L of 0, which is to say 0. Which tells us that by uniqueness of additive inverses, L of negative V is negative L of V. Yeah, Mia.
Oh, I was just, could you also just say that alpha equals -1 and then use the rule L times alpha V is equal to alpha L times V, or alpha L of V?
Yes. Yes, I think so. Yes. Yeah, that'll do. Yeah, that's good. Okay. Okay. Other questions? Other questions? Okay. Couple more ideas. Couple more fundamental ideas. Let's see. Yeah. So kernel and image. So again, you have T, a linear transformation. The kernel of T is defined to be everything in the original space, in the domain space, such that it gets mapped to the 0 of the second space. Okay. It's just like the null space. Do you remember? We had these matrices, right? This is basically analogous to the null space. Right. The kernel of T sub A is the null space of A. Back in Euclidean space, right? The null space was everything that got killed by the matrix, right? Everything that got killed by the matrix, everything that gets killed by the transformation is the kernel. Okay. It's basically the same idea.
Yeah.
Okay.
Okay, I feel silly asking
No, no,
this,
no.
but the null space of A is it usually like 0, like for linearly? I
No.
forgot what the null space is.
The null space is everything that gets killed by the matrix. So like all answers to this problem.
Oh, okay,
Right?
yeah, that's
all
what I
ans
meant.
all x such that ax equals 0.
Okay, and then the kernel would be all.
It's basically the same thing. Everybody such that t of v is equal to 0.
Okay.
It's basically the same idea. Basically the same idea. Right. I mean, we could it would have been perfectly okay to talk about the kernel of A. Instead of calling it the null space of A, we could have called it the kernel of A. Everything that gets killed by left multiplication by A. Haley.
Will the kernel send V to 0 as well?
The kernel is a space actually. It doesn't do anything. It's a subspace.
Space. So you're multiplying the kernel by transformation, right?
No, this is just notation. This says the kernel. The kernel of T, denoted ker T, is defined to be all vectors in V such that T of V is 0.
T of V is
Yeah.
0?
So
So it's not T times V?
T times V. Well, T of V, really. T of V. People usually just write TV and leave the parentheses off in linear algebra.
But like the difference is that like the null space you're multiplying it by something, right, to get 0?
Right. So back when we were talking about matrices, then we were saying you take this guy and then you hit with the left multiplication. Okay. So for example, maybe this will clear things up. Like the kernel of the differential operator, right? It's not left. The differential operator doesn't. The derivative doesn't act by left multiplication. It simply acts on the space of polynomials, right? So you've got D. It goes from Pn to Pn minus 1. The kernel of D is going to be the constants, right? All constant functions, right? Because they get killed by differentiation. They get sent to the 0 function by differentiation. Okay. Second notion, and this is a little bit tricky because the book defines it in a peculiar way. So S, a subspace of V, T of S, the book says this is going to be all W in the target space such that W equals T of V for some V in S. Okay. We call this thing, the book calls this thing the image of S under T. The image of S under T. Okay, so basically what this is you take all elements of S and then you run them through T. And that collection is T of S, right? You take all elements of S, right? You've got the subspace S, and you see where T sends everything, right? And the collection of all outputs is called T of S, the image of S under T.
Can you say that again?
Yes. So actually, let me give you an example. If I'm looking at D acting on the whole space P sub n, well, the image of D on P sub n is going to be all outputs that I get by letting D act on P sub n. Well, what's it going to be? It's going to be Pn minus 1, right? Because the collection of all outputs is going to be all, these are the guys of degree less than n. I'm going to get the guys less than degree n minus 1. Right? Or going back to this guy, which was projection downwards, right? If I look at L's action on the whole space, right? L's action on all of R2, what do I get? Well, I get this thing here, right? X0, where X is in R. right? And so the image of L on the whole space is going to be just the x-axis. So it's just like all the outputs, the collection of all outputs, when you restrict your linear transformation to this particular subspace. If we look at the rotation guy, right? We're in R2. We take some subspace, right? Here's a subspace, right? This was some subspace S, right? And then the rotation guy says rotate by some angle, right? And we get a new subspace, right? T theta S, right? You look at all the vectors in S, and you rotate each of them and look at that collection of all the outputs. That's going to be the image. Okay, Charlie.
So by definition, any transformation of V is a subspace.
Any transformation, what?
Of like anything in the vector space V is going to be a subspace.
It will, if you start off with a subspace and you run it through a transformation, if you look at the image of a subspace under linear transformation, it will turn out to be a subspace. Yeah. Is that what you're saying?
Yes, yeah.
Okay, yes, okay, yeah. So, yeah, that was going to be my next comment, that in fact the kernel and the image are both subspaces. Kernel and image are both subspaces. They're both closed under addition and scalar multiplication. Let me just say one last thing. In the book, they call T of the whole space the range of T. T of the whole space, they call that thing the range of T. That's sort of unusual. So my understanding is that usually one calls this the image of T. So when I hear image of T, what I think of is the image of T acting on the whole subspace. The authors call that thing the range, and they call these sort of partial guys the images of subspaces, images of subspaces under the linear transformation. Okay, but generally I don't even have a term for this, and I call this thing the image. So, but I'll try to make it clear what I'm saying when I use the term. Generally, yeah. So for me, this is the range, right? This is the range, and this is the image, right? This is the range, and this is the image. But for the authors, this is the range, and then image is used for the image of some subspace of V. Okay. Anyway, I think it's more common to call this thing the range and then this thing the image. Okay, just to tell you.
Why did the book do it that way?
I don't know. There may be some. It may be that later on it's more convenient to have this language, but at least in this course, I don't think we. In the parts of the books that I've used, I haven't